And this is a project that I have been doing with my supervisor Ashok and a student Swapnama and a postdoc Richard for around 2.5 years now. And we published maybe 2 papers. So before I go to the next slide, so let me say what I'm planning to do here. So I'm going to give a broad overview of what is microstate counting, and then I will present the work. And then I will just touch upon some of the silent features of this second paper, but then I will skip most of it for NSM and then go to some futuristic thing that we have been trying out, this Hilbert series. So yeah. So as we know, basically that classically these black holes are thermodynamic objects and they preserve the second law, they have entropy. So if they do not have entropy, then you run into various thought experiment problems. You throw a bucket of water, where does the entropy go? The neutrons can collapse, what will happen? All the microstates are there. And these are the kind of questions that you won't be able to answer unless you have a black hole entropy. And we also know that black hole entropy is basically black hole area. And now we also know, thanks to string theory and maybe to some extent to quantum gravity, that there are corrections to this.
Which gets the corrections right?
I have been doing string theory for 4 years, so I think string theory gets it right.
You're a brave man.
So this is all okay, but then
maybe I should have asked which, according to your advisor, gets it wrong.
I should probably believe that quantum gravity is wrong.
Joke.
So what is the statistical interpretation of this black hole entropy? So again, we know that classically, if you have a black hole, it is fixed by a very few parameters, say mass, charge, angular momentum. So, and there are lots of uniqueness theorems in classical black holes. So you basically cannot get much degeneracy if you just fix these quantum numbers, not quantum numbers, this mass, charge, and angular momentums. So this cannot basically account for the large entropy that you have. So you have to go further than the classical picture, and you have to look at the microscopic theory or the theory of quantum gravity. And this should provide you, among other various other things that might interest you, the black hole microstates. So black holes must have microstates. So this is where I think string theory should fit, mainly because I have been doing it for 4 years. And so why string theory basically becomes important in these problems? It is mostly because of this following reasons. So basically, if you just start with the strings, if you quantize it, you get lots of 40% fields. And then you get a large massless sector from various objects in string theories. But usually, if you look at superstrings, it is 10-dimensional. But you never really basically work in 10 dimensions. You always compactify the theory to some lower dimensional, 4-dimensional theory, because we more or less know that we live in the 4 dimensions. And then if you do this, because of these compactifications, there are furthermore massless fields and a lot of gauge fields also. And now, this risk 2 decades development, there are these new objects in this theory called the D-branes, which are charged under these gauge fields. And they also have this dual interpretation that they can also be the sources for these fields. And these are very important objects. At least they are very, very important for black holes. So what looks like this charge object, maybe the black holes in 4 dimensions, they have a much richer content living in these extra dimensions. And because we have something like this, we can make a statement that in string theory, black holes have these microstates hidden in these extra dimensions. So let's elaborate on this. So So basically, when you say black holes in string theory, you basically have two pictures in mind. So one is called the microscopic picture, which is basically the quantum picture. And then there is this macroscopic picture, which is basically the classical picture. So let's say the classical picture, the macroscopic picture, what you should have? You should have a large black hole which has a moderately low curvature at the horizon. For these things, you basically need a small g and a large ga. And then you basically also need a strong coupling gs, because this gs basically will characterize what your g, this Newton constant g is. And then you have a microscopic theory. In the microscopic theory, you should be able to calculate something quantitatively at least. So you should have gs to be small, so that you can switch off gravity and do some calculations there. And this is exactly the quantum regime. This is the regime where you have, as black holes is replaced by some Riemann system on which some strings are fluctuating like this.
And this GS is not the closed string coupling. What is GS?
GS is the string coupling. So
is it the closed string coupling?
it doesn't matter. E to the power 2 phi is GS.
I thought if we had closed string coupling large, we wouldn't be able to control the macroscopic side. Would we have a lot of string loop corrections?
Yeah, that's why small g. So you on both sides you should have small g, but which one is smaller? So the microscopic side should be smaller.
Wait, so capital G is a dimension full object, right?
Capital G.
Newton constant. What a small g I don't understand. It's some dimensions. Large G I might understand.
The small g is the string coupling. So this basically G is there is some
small capital G. Capital G is the string coupling.
This is the string coupling.
Correct. So just the first line, small capital G, I don't understand because that's dimension 4.
I think he means a small gn. The dimensionless thing made out of mass.
So gn by r, that part.
Basically, the gravitational radius should be small compared to string length.
In the microscope.
In the microscope.
Curvature will go like 1 by.
And in the microscopic side, it's going to be large.
Yeah.
But now suppose it's large. You've got a large black hole and you've got very strongly coupled strings. Can we still reliably? Is it still reliable? Is the Bekenstein-Hawking formula still reliable?
From the as long as supergravity is reliable, you can do loop corrections there to the black hole entropy. That is what the whole loop correction business in microscopic side is.
I think you're not suggesting that on the gravity side, when the supergravity description is valid, let me correct. I think what you're saying is when the supergravity description is valid, quantum loop corrections are small.
Yeah, but they are there. If you want to calculate it, you can in principle calculate it.
Yeah, but they are controlled by GS, which is small.
Yeah.
However, when you say it's strong coupling, you mean it's GS is small but large enough so that capital G times M is big.
So that
actually, you're not saying GS is much greater than 1.
No, just big enough to make capital G.
And that's why I wrote small g on both sides. So one of them is relatively small.
I see. But just to ask, suppose we're in a situation where the black hole is very large compared to blank units, but GS was order 1. Do we have a reliable formula for black hole entropy in that situation?
GS is order 1.
Just solve the classical Einstein equations would be totally reliable.
Well, I was just thinking that sometimes the fact that you got square root GR is a universal dimensional analysis prediction. So apart from possible normalization of Newton's constant, all such effects may be. I'm not sure.
So what is the goal here? So the goal here is in string theory to compare these two regimes. So basically, string theory has both the classical side as supergravity and the quantum side as dyons. So you have to somehow connect this.
Sorry, that's probably the non-local stuff that you would be able to do. I think that's the point. But the local stuff, the world stuff would be okay, but the non-local stuff would not be under control. Like the loop corrections, like the logs.
So you were saying the massless loops?
Yeah, exactly. The non-local stuff would go out of control, and that Okay. Yeah. Sorry.
So mostly in string theory, we concentrate on extremal or stable black holes. These are black holes which basically have zero temperature and they do not propagate. So at least they are not going there. Now on this extremal black holes, you can calculate certain quantities for the Witten or BPS index, and they are protected in the sense that if you change the coupling GS, these things should not change because they basically are telling you how many states are there and number of states cannot jump. And so basically this on both sides you have the supersymmetric black holes or a supersymmetric Hilbert system, and so generically people call this the BPS black holes. And BPS index of black holes, mostly up to some signs, is always black hole entropy.
And that's partly something we will talk about, or I mean, I know there's a whole story.
This is a whole story.
That's not what you're going to talk about.
So basically, because I can give you the reason. So basically, it is because angular momentum turns out to be zero in most cases, and there is a -1 to the power j factor in most index calculations. So because j is zero, the other thing is essentially nothing but
Entropy number and index.
So this is a case-by-case argument, looking at various examples and seeing that this is what happens.
Yeah, this is what happens. And this is what happens we know from the DS2 geometry of the extremal black holes. This is mostly from there. Because you have this DS2 near horizon geometry, it also has this SU1, 1. So it basically tells you that it cannot have any. Now, what have we so far achieved in string theory? So, for a wide class of this n equal to 4 and n equal to 8 supersymmetric string theories, this microscopic and macroscopic matching has been done, and this is a real success story in that sense, because at least in string theory we do not have any experimental prediction, so as any theoretical prediction is always welcome. But what remains is this n equal to 2 theories, and specifically n equal to 2 theories are the theories of this Calabi-Yau compactifications. The black holes there, they turn out to be very complicated in terms of the microscopic structure, because not only single centers are there, usually there are lots of 2-center, 3-center, multi-center contributions come in the index, and you have to basically keep track of what is going on. So it has not been done. It is difficult to do. So what we are trying to achieve here in this big project of ours is to somehow able to develop some kind of new formalism to count directly these microstates in n equal to 2 dimensions.
Can I ask you something? Wasn't there a formula injected by Kansevich or somebody else?
Moon has their formula, but that is not in the black hole limit. So the limit was like one of the charges going large, but the other charges remain small. But to get the black hole limit, you have to have all the charges going large, so that you have a radial. The curvature is basically small. So to have a black hole picture, you should have a curvature. Black hole which have curvature small. If you have a very tight curvature, then you should have a lot of loop corrections on top of that, also in the superduality side. So that is not really a black hole, effective black hole picture. Effective black hole picture is something in which you have.
So for that regime where you expect a smooth black hole, there is no conjecture formula also. It's completely uncharted, open.
Which one?
N equals 2.
With the wall crossing formula of Constellation Entanglement, I thought was quite general.
So that's what I'm asking. Doesn't that give a...
Yeah, but after that, if you take the charge, so they have used as a set of charges.
Nice.
So if you can scale all the charges, then it is okay. That is the black hole limit. But that you cannot do.
There's out of ignorance. The wall crossing formula of Constellation Entanglement applied only with some restriction on charges or general? My very ignorant. What I heard was
I also don't know. Yeah, I also what I heard.
I also heard, but again, I know it. Nothing really, very little.
But of course, maybe going from wall crossing to actual number requires you to be able to control some other end. You have to be able to start somewhere where you know the answer and then cross out the words. Maybe that's it. Because they only had a formula for the jump, not for the answer.
Yeah, I think they proposed a closed form of the answer only in some certain limits.
Sorry, I did.
Yeah, so the goal was here. So if you have this n equal to 2 black holes, that is Calabi-Yau black holes. So there is a very important property in Calabi-Yaus that Calabi-Yaus do not have any one cycles. So if they do not have any one cycles, you cannot have strings wrapping them. So if you cannot have strings wrapping them, you cannot have momentum going along those, cannot have wrapping going along those. This basically means the charges of any charges of the theory can only come from these deviants. So that is why the main focus here is to look at a system where the charges of the system are only given by the deviants. So basic idea again is nothing but to calculate the Witten index of the theory living on this intersection of these deviants. So how to proceed? So what we have done is we have not touched Calabi-Yau. That is a foreign pretense. That is something we want to do. What we have done is much simpler. We have this 1/8 BPS black holes in n equal to A string theory in type 2A, and people know answers for this. There are dual systems of some KK monopole and D1 D5 P system in which Tominga, Rain and Ashok they have basically calculated the microscopic index. Knowing the answer from there, you can do various duality transformations, space duality, G duality, and come up with a system which has these 4 deviants. I will just mention the system a little bit later, but this is the thing. So what we are trying to do now, is to, even if everything is conjectural, what is good about this whole thing is that you have another example in which U-duality works. So U-duality, as you know, this is a conjecture in itself. So more and more proofs that you can give is better. So for this, so basically what you have found is that for certain charges that we could actually calculate, this 1/8 BPS black hole that we have constructed in terms of these deviant systems, and the one that is known in the literature as a U-dual of this system, basically the microstates match, the number of microstates match. But the way we calculate is very, very different from the way the calculation was done earlier. So it's completely redoing of everything that was done.
See again, so you look at basically toroidal compactification, but you look at a system consisting of intersecting deviants, and you do a calculation in a very different way with an I, so that maybe in a Calabi-Yau.
Yeah. So ultimately, so the point is that we know that the usual formalism that we have developed so far is not very useful for the Calabi-Yau. So we will have to develop something more to basically tackle Calabi-Yau's right.
And again, I'm really sorry, I should wait, but I mean, in the end, you are going to get a quantum mechanics, right?
Yeah.
So the supersymmetry is not, it's asked this, obviously the answer must be no, but it's not tight enough that, okay, now that you know what a Calabi-Yau is and so on, you can write down the quantum mechanics. You may not be able to solve it, but
in Calabi-Yau,
in
Calabi-Yau, this whole thing is much more difficult, because the thing is that first of all in Calabi-Yau, this kind of picture that you have deviants and string fluctuating on that and you quantize this kind of system, this itself is very difficult to do in general in Calabi-Yau. First we have to somehow do these things and figure out what is the spectrum of the theory. Then we can basically figure out what to do next, because in Calabi-Yau also you have to have specific cycles in which the supersymmetry will be preserved, and if you do something else, everything will be broken.
Orbifold limits you could figure out.
Yeah, that is the next thing we are going to do.
Yeah.
That is the next thing we are going to do. Yeah, so basically say if you take K3, K3 can be typically described as D4 by Z2. So those are the kind of things that we will now do. And if we succeed in doing those things, then we can lift those techniques to Calabi-Yau parity. So, in summary, the whole problem basically boils down to computing Witten index, as Sandeep mentioned, on the intersecting driven system. And this basically again boils down to counting the number of solutions of some matrix equations subjected to some complex proofs. So this GL N1C, these are this matrix, general matrix group. I do not know the proper name for them. This is basically, if you have a matrix group, these are complex entries in N1 cross N1 matrix. And the result that we are now focusing on, so Calabi-Yau is kind of far away, but the immediate result is that it seems that all the microstate that you find from this system carry zero angular momentum. And this leads us to be conjecture that at generic points in the moduli space, microstates of these single-centered black holes all carry zero angular momentum. If this is true, this is a major jump, because we know from the macroscopic side that this is something which is true in the sense that in the macroscopic side, in extremal black holes, you have this ADS2 cross S2 factors, which basically tells you that there cannot be any angular momentum. Because S2 basically has SO3 isometry, so that basically means that if you have to have this SO3 isometry, you cannot have any angular momentum here. This we know from the macroscopic side, but it so happens that if you do the calculations in the microscopic side, the states that you get have lots of angular momentum, some positive, some negative, and there is really a very precision calculation going on there, which basically cancels the positive angular momentum states with the negative angular momentum states and give you a small number for small charges. And these extra cancellations, basically, I do not think anybody understood why this should be there, but it seems that it might not be there, and it is an artifact of the of putting the system at not generic points in the modular space, but at some special points in the modular space. And if you put the system in a generic point in the modular space, you do not get this. And just to mention here, because this statement is actually very important, this conjecture puts very strong limits on the fuzzball book. So far, I know very little about fuzzballs, but so far, all the solutions that I know or have seen for different systems or for systems in which these fuzzballs basically are supposed to mimic a black hole microstate, all those have non-zero angular momentum. Generically.
Do they have fuzzball type geometries for your system?
I don't know, maybe someone could come up with this.
No,
but there
you're not aware of.
No, there are fuzzball systems in which there are no angular momentum. But generically, they do not correspond to any D1, D5 system or any kind of black hole system. So they basically come from stringy objects.
Yes, you tell us that your quantum mechanics, does it have two branches, like a Higgs branch and a Coulomb branch? Or just unique vacuum?
This basically is n equal to 1, so
so there's nothing like that. Right. So then I think you should expect that there are no fuzzball type geometry. I mean, the rough idea was that the fuzzballs were sort of like the Coulomb branch, and the black hole microstates were like the Higgs branch in the cases where it had been worked out. So here, if you don't have the analog of that, maybe there just aren't any fuzzball geometries.
Yeah,
in your system.
Yeah, but
that itself would be a radical statement from the fuzzball program.
So, yeah.
the whole program will be cut.
No, I mean, of course, they haven't made the statement, but yeah, this would, if you feel you have an understanding of what the role of those fuzzball things, then that would be a prediction.
They would probably
say we do not want to make such strong
then that's fine. I mean, okay, so it's a prediction.
Okay, so maybe now I will move to our system. So our system basically consists of this D2, D2, D2 and another D6 plane. And this D2 is wrapped along 4, 5. And this 4, 5, 6, 7, 8, 9, they are the compact direction. 0, 1, 2, 3, 0 being the time, and 1, 2, 3, these are the non-compact directions. So first D2 is 4, 5, the second one is 6, 7, the third one is 8, 9, and another D6 will basically covers 4, 5, 6, 7, 8, 9. And this basically describes a 1-8 BPS black holes in n equal to 8 theory. So for those who do not know, so how it is 1-8. So basically if you put the first D2 plane, it breaks up the supersymmetry from 32 to 16. Then you put the second one, because the second one is completely orthogonal to the first one, it again breaks half of this. So from 16 to 8, and then 8, 9, then 8 to 4. But then these 4, 5, 6, 7, 8, 9 are common directions to these 4, 5, 6, 7, 8, 9. If you know the projection matrices, gamma matrices that comes in this calculation, you basically can convince yourself that this D6 will not break anything. So this, even though there are 4 D planes, this is basically stopping at n equal to 1. So what to do here? So what to do here is to, as I mentioned, calculate the Witten index. But how to do? So basically, you just take the zero energy modes of these string fluctuations, both this kind of string which aims on the single plane and kinds of string which basically aims on 2 planes. You basically quantize, have a spectrum from this, the massless spectrum, and just write down the supersymmetric action for it, and then you come to this. So ultimately, what you can see that the common direction that all this D-plane system has is only the time direction. So basically, as Sandeep pointed out, this is a quantum mechanics. So you basically have to calculate the Witten index of a supersymmetric quantum mechanics. Yeah, as I mentioned, you calculate the spectrum. Then you got the spectrum, but then from the spectrum, you basically, it is always very useful to organize your things in terms of multiplets. So you have the spectrum, organize the spectrum in terms of various supersymmetric multiplets. Now, because it is SUSY basically dictates a lot of the interaction terms, plus the kinetic term is completely fixed by these things. So there is not much freedom going on in SUSY except for one freedom, that because this is n equal to 1, you still have a freedom to choose a superpotential. And we will see that this is very, very important that you choose a superpotential. And then you basically calculate the Witten index for this thing. And we know from Witten that Witten index in quantum mechanics of supersymmetric quantum mechanics, Witten index is essentially mapped to cohomology of the vacuum manifolds. So essentially you can map the whole system here, and that is why basically the reason why the Witten index exactly gives you the Euler characteristics of all this.
I would love to separate these D2 branes arbitrarily to preserve supersymmetry.
Arbitrary means this intersecting nodes.
Right. So the D2 branes are, each of the D2 branes are a point in D4.
So yeah, this doesn't really matter whether this is here or this is here. These are all the zero modes of the system. And you put this thing here.
But are you going to require that they all meet at a point or not? So the D2 branes can be anywhere.
You will see that the most of the interaction is basically there because of this pairwise D2 branes.
Well, if the D2 branes are separated from each other, then the strings stretching between the two of them are massive.
Yeah, you basically you will not take those strings. Right?
So the only fields
Only
that
fields
matter are
the
the
master
two branes to the.
So if you take this string and do a quantization, you will get a lot of massive modes.
I understand. I just want to know your quantum mechanics. Which modes is it?
Only the zero modes, the master.
Which are the zero modes? Do they include modes from one D2 brane to another?
These are the modes from one D2 brane to another.
Are they massless?
They are massless.
That means the D2 branes are meeting at a point, right?
Probably you have some Yukawa, right? when you're in the Coulomb branch, I'm just thinking, then the bifundamentals will get a mass.
Or you are saying that whether you can completely separate them?
Yes.
No. Sorry, no.
But what does it break supersymmetry if you separate them out?
This is becoming massive. That's why.
It's fine if it becomes massive. I'm asking. I'm not clear.
I don't think it breaks.
If you were to write down the field theories, you would have adjoint degrees and you would have bifundamentals and you would have Yukawas. So if the adjoint degrees had waves, the bifundamentals would be getting a mass. That would be part of what comes out of the field theory also. Right?
Ultimately, you will get mass terms. But to begin with,
you don't have masses, you only have the Yukawa type.
Yeah.
No, but then you're going to get a manifold of vacuum. Classically, you get a manifold of vacuum ion system.
That is what we are supposed to get here.
And you will see.
But
it will come out.
It will come out, but there are surprises there.
But then presumably it will get lifted or something.
That's what I was asking. Whether that there's only one really supersymmetric one that they're already at.
Yeah, so it will
Whether the superpotential basically.
Yeah, it will come out that if this Takwa that was saying, they are just collection of points.
So that means that you cannot separate.
Yeah. So if you separate them, they are the massive modes.
No, you see, if you separate them, then some other modes become massive. That doesn't mean that you cannot separate them. If you take D3 branes together, you can separate them. The modes between them become massive. All of these are supersymmetric. So I want to know whether
supersymmetry won't break, but
if you're saying there's only a discrete collection of points, then you must be saying that this mode breaks supersymmetry. Because otherwise there's a line of supersymmetry.
why so?
Because if you can separate the two branes by arbitrary amount, then there's a continuous parameter. And if that preserves supersymmetry, then you don't have discrete supersymmetry vacuum.
Yeah, but if I get massive multiplets, if I just separate them, this would
The massive multiplets are for the strings between. See, it's like D3 branes. Suppose you've got D3 branes, you can put a system of two D3 branes, you can put them at any separation. The strings between them become massive, but that doesn't mean that this configuration is not supersymmetric.
Yeah, configuration.
So you have a moduli space of vacuum. Now what you are saying is there are only discretely many vacuum, which must mean that the separation parameter breaks supersymmetry.
Why does it break supersymmetry? I mean, if you separate them out,
so I think what you are saying is that the quantum mechanics per se includes all these degrees, and then you will analyze the quantum mechanics and find where the supersymmetric minima lie.
Yeah, that is usually that will do, but
and then you find a discrete number of minima, right?
Discrete number of minima, right?
So it's only n equals 1 supersymmetry, so you can have all kinds of complicated
Superpotential.
non-observative even effects. I don't know what will happen.
Yeah.
But this could easily happen. There are classical moduli spaces.
but just by looking at the supersymmetry charges, the way you have done it, if you section them, the way they are oriented,
They are all orthogonal to each other.
Yes, so therefore, if you separate them, it doesn't look like that that subset of the supersymmetries which were, which are preserved at coincidence, anything will happen to them, right?
I do not think supersymmetry will break if you separate.
Then why do you have only isolated points as your backward? Why don't you have a line? Why don't you have goldstones which preserve supersymmetry and therefore you have a line or you have a manifold of supersymmetry?
So if we are looking at the spectrum, we can, if you separate them, you have massive hypermultiplets.
Now that's a different issue.
But we are looking at the zero modes.
When you say if you separate them, you don't break supersymmetry, is that a classical statement or is it a statement in the full quantum theory?
It is a statement in the full quantum theory.
Yeah. So then you have moduli space of vacuum.
That's what I'm saying. I have a moduli space of vacuum, but it so turns out that this moduli space is zero dimension.
Which means you don't have a moduli space.
But
only a set of discrete points.
Yeah, but this is very essential that we have a set of discrete points because that basically will give you the zero angular momentum states.
Sure. But I'm saying finally you will have only a set of discrete points.
Right. There is no continuous parameter.
So in that sense, you don't have a continuous moduli space. So this can happen, right? Classical moduli space are lifted all the time.
But it's some or you know some effect.
Yeah, I will include interactions which basically will do this job. Without the interactions, so basically if you do not include the superpotentials terms, you will get certain vacuum which basically have a continuous parameters. We do not want that. We basically wanted a system in which you basically get zero angular momentum states.
But in the end, the debrains are forced to sit on top of each other, is what you're saying.
Yeah. Actually not. That is also not correct because the separations of the debrains are fixed in terms of...
Okay, not just on top of it. There are some particular separations that they force.
Yeah. Right. So that is not a moduli parameter. The separation of the brains is not a moduli parameter. Okay. So the field content. So what is the field content? So suppose you take one of these branes. You know that in one of these branes you should have this n equal to 4 super n. So basically you have this in the same brane. You have this gauge field and the Pi, Qi, Ri. These are the transverse directions. All the complex. So there are 6 directions. So if you complexify, these are 3 directions, and they are in the adjoint of UN. And then there are different branes, which basically are these strings. If you quantize them, you get these bifundamental Zij's, which basically means if you have a gauge group here, if you have a gauge group here, they transform as n of one gauge group and n bar of the another gauge group. So this basically is the anti-fundamental fields. So what are the interpretations? I already mentioned this D1 basically is the coordinates of the first plane, and this P1, this one set, it is completely up to you. One of them are the Wilson lines. So for example, if you have the 4-5 plane, so anything going along the 4-5 direction, any gauge field going along the 4-5 direction, if you compactify, it becomes scalars, and they basically are the Wilson lines. And then there are these transverse directions Q1 and R1. This basically is the interpretation. So what can you say about the system? So basically we have a string.
So your gauge group is UN1, that's UN2, that's UN3, that's UN4.
Now,
and
for now,
you've got bifundamental matter between any two of them.
Yeah. So for now I am looking at the complete general setup, but you won't be able to solve anything in this setup. You have to boil down to U1 cross U1 cross U1 cross U1. Yeah. So a string can only see these two branes at once. So basically, if you want to write down a Lagrangian,
each pair is like a 0-4 system, right? Because 2 brane and 6 brane, you dedualize the 2 directions, it becomes 0-4. And 2 brane and orthogonal to
the D0 D4 system, you say.
Yes.
Yeah. And we have used that, in fact. Because a lot of things in the literature has been done in D0 D4 system. You don't have to repeat a lot of calculations.
So at least the matter content comes immediately from that.
Yeah,
0-4 string.
So this is very important that you have this D0 D4. So maybe I should explain. So because you have this D0 D4, as people know, that why D0 D4 or D1 D5 is important. This is because unless you have this 4th direction in which you have normatively stepped boundary condition, you do not get massless fields. So to get massless fields, you basically need this.
So pairwise, the matter content is that of an n equals 2 theory.
Yeah, as I am going to mention that. Yeah. So that is an equal to 2 theory. And you can write the Lagrangian for n equal to 2 theory for this pairwise Lagrangian. So for each brane, I'll mention it first. So for this mixed string, so this Z12 and Z21, these things coming from this, they talk to basically the separation of the branes. So this is the V1 minus V2 and R1 minus R2. These are the gauge field separation and the other separation of the transverse directions. And the Goldstone modes of the whole system, which basically is moving the whole system up and down, or moving one of the planes in terms of the other plane. These are all. Yeah, so these are the Goldstone modes. So the point is that these Goldstone modes are massless modes, and you won't detect these modes in the system. They are basically flat directions. They won't couple to anything. And for this different system, these are flat directions. You can also show that if you have this different system and go to the black hole picture, these are also flat directions for the black hole picture. So this basically means that you move the black hole in some direction. So essentially you are not interested in this. So you will factor out these modes.
There is no direction which is common to all the planes, right?
Sorry?
The 4 transfer.
One of them is there. 86 is there, which is common to all the planes means.
I mean,
pairwise they are common.
Oh, pairwise, yes, but ultimately for the black hole, if you're looking, then you want something which is common to all the planes, right? I just didn't understand your last comment. Pairwise, of course, there are common directions, but if you take the full assembly, then there is no direction along which you can just transfer.
Common transfers. The remaining R4.
R4, of course.
So you have this compact.
Sorry, I was just thinking of the compact direction because you grouped them together. Yeah, besides these 3 complex directions you have, of course.
Okay, so now if you have the Goldstones, you also have the Goldstinos because you have this n equal to 1 supersymmetry prism. So you do not. There are 2 ways you can get this. It is very important that you get these Goldstinos right. There are 2 ways you can do this. You have the Goldstones. You know that it has multiplet structure, each of the things. Then you just figure out what is the corresponding multiplet fermion for that. Another way is to write down the full Lagrangian and see which of the these fermions are basically not picking up any mass. And those are the Goldstones. Why it is important in the sense that first of all, the number of Goldstones Goldstinos will basically tell you how much supersymmetry is, because this is a cross check that you have the n equal to 1 supersymmetry. So basically this will tell you how many of them are broken. And another thing is that when you calculate index in black hole, you also factor out these Goldstinos. So in the macroscopic side, these Goldstinos basically sits at the boundary of the black hole. For the horizon modes, there is no contribution of any fermion from in the horizon excitation. So from the macroscopic side, we know that Goldstinos won't come. And these Goldstinos, you have to factor out from this whole thing. So if you do not factor out these Goldstinos, this basically means that for each state, you will have a complete hypermultiplet of states created by the broken supersymmetries.
So your full Hilbert space is a tensor product of free Hilbert space
of this
and whatever you get from
it. So that throw away the trivial part. Yeah. So basically, I think in literature they call it Apple microstate or something. Okay, so now coming to the Lagrangian. So for each brane, you have n equal to 4 supersymmetry. You write down a super element and then compactify accordingly. These directions get compactified. For each pairwise brane, as Siddharth pointed out, it is n equal to 2. And for n equal to 4, you completely know the action. N equal to 2, you completely know the action. What is going to be up to the superpotentials.
This 2 has no super.
I mean this part.
Oh, up to the n equals 1.
No, this I am calling this superpotential because technically they don't have any superpotential. So you should not call it superpotential. And I am basically this Q phi Q. So hypermultiplet and the adjoint coupling.
That comes from you.
Yeah. That is there. That has to be there.
Yeah.
So
I'm calling that. I'm putting that in the superpotential.
You're writing it all in n equals 1. So
because I have to basically look at these things and then figure out what are the these supersymmetric factors. So yeah. So basically for n equal to 4, you have for the non-abelian part, you have something like this. PQR, you know this from the super unit. For n equal to 2, you have this hypermultiplet, phi, hypermultiplet kind of coupling. And this is the part that you have to add by hand.
The part that knows that you have not just pairs. Three things.
Which what three things?
This involves three different brains, right? These Zs.
Oh, this, yeah. You can also have four rows.
More than two.
Yeah.
And how do you add this up? How do you
Okay, that time.
This is a sort of non-trivial thing, right?
Not completely non-trivial, so maybe let's see if I have the slide for it.
It's just the class.
Okay, let me say. So why we add this? So the point is that you know that this kind of term should be there. Because if you have these two brains and you have another brain coming out of there, a string can go from here to here, come here and go here. So this Z kind of thing has to be there first of all. Now how to motivate that this is what should be there.
That's not a single string, right? A single string would have just two brains on it.
Yeah, but you can 1, 2, 2, 3, 3, 1.
You said you could write an interaction, a scattering amplitude.
You can write something.
There will be a paired scattering amplitude.
So this kind of things will ultimately give you Yukawa kind of stuff.
But is that what you do, or do you look at some diagonal?
Yeah, so let me come to that. No, we have to look at that to fix the signs. So in the first paper, we missed the signs. Frankly speaking, we didn't look at it carefully. In the second paper, it turns out that the signs are very important. The signs are very important. Maybe the structure is there.
Got the answer.
Yeah, the answer is right. So the signs are important in the sense that it was not important in the earlier case because you have n equal to you have u1 gate groups. So the earlier paper was u1 cross u1 cross u1 cross u1. Now we have replaced this by u2 and u3. So this was abelian completely. This becomes non-abelian. Now this has major consequences. So the point is that because it was abelian, this term was not there because they are adjoint. Because these terms are not there, the point here, the whole point of this signs is to how do you know what is the relative sign between this term and this term. You do not know. So the point is that if you have a sign here, you can always pick this sign inside these z's by some scaling of the z's. But then this z scaling should affect some other things. This z scaling would affect this Wn2, and this will affect in turn this r. This r will again affect this. So there is a chain of things that basically affects. Now the point was that if this term was not there, so it only affects up to this, and then there is no effect on here. See, if there is no effect here, I could have always put this minus sign inside of some of the z's. That would be consistent. And that is why in the earlier case, in the u1 case, though we have missed the signs, we got the correct answer.
But just forgetting what signs are going, what about the magnitude of that?
Yeah, magnitude we can calculate.
How?
Okay. Do you want to go into this?
No, just a sentence.
Yeah, so the point is that you basically calculate vertex operators of open strings.
So string scattering axis, right? You compute the scattering of these three nodes, and from that you feed off that.
Yeah.
Okay.
The point is that, but there are caveats there. You know that there are various co-cycles and other factors that are there in this kind of z.
And that usually affects signs.
Yeah, that usually.
Let's forget about signs.
Yeah.
Okay.
Up to the signs. If you forget about signs, this C turns out to be 1. And these signs are basically now fixed by some other secondary arguments.
Actually, yes.
Hello?
Hello, yes. So what does C stand for?
What?
C.
Oh, C is some number.
The number. Okay.
This C, right?
Yeah, and the small C12 is also a number?
All C's are number, but they have different interpretations. So the point is that, yeah, so let me explain as Sandeep asked this, so let me explain this. So these C's, the things that you see as C12, these basically are related to small fluctuations of constant G mu nu and B mu nu backgrounds. And so basically what you do is that you have the system. Now part of the system with small G mu nu and B mu nu constant backgrounds. And now again re-quantize everything here. Do all these things again. You will see that you naturally will get mass terms for these Z's and these other things. So if you get mass terms, they somehow have to generate these mass terms from this superpotential. So up to this, if you have the theory up to this, there is no scope of generating any mass term. So you know what you have to write down n equal to 1 superpotential term to generate the mass terms. And then it is mostly guesswork that if this is the structure, then you can generate the mass terms, and those mass terms exactly connects this C12 with the background G mu nu and B mu nu fields. So this is a completely consistent picture.
I'm sorry, I missed this. R1 and R2 were like some transverse.
R1, R2 are the fields. So R1, R2 are the transverse direction. Yeah.
Transverse directions. Sorry, say again, how do you get that C1 to R1, R2?
Yeah, so basically
is that sum over IJNs and ZIs and Js?
This is some. Maybe a K should be.
K should be there, and that sum doesn't apply on that big square bracket.
Sir, I think it's got disconnect.
Well, it should reconnect automatically. Yeah, I'll call that.
It's back.
Hi, can you hear me? Can you hear me?
Can you hear?
Yeah.
Okay. Yeah. So what was the question? Yeah, there are other terms like R1, R2. There are other P's and Q's, right? So they are there.
So that square bracket is C1 to R1 minus R2 plus C2 3 R2 minus
so all
R3.
these things are there.
Now ours were each brane had its transverse fluctuation, right? So which R is the transverse fluctuation of which brane?
It doesn't really depend on what the name doesn't matter. One of the branes, I think.
Wait, R of the 1 and 2 refers to some directions or to the brane?
Oh no. This 1 and 2 are the branes. These R's are the same direction.
R is one of the directions.
So this is the difference. This is what you were saying, that the difference between the branes. So
yeah.
This difference between the branes will be fixed in terms of Z's. If you do the if you get to the moduli space, this is what will happen.
I see. Now this already tells us that R1 not equal to R2 is breaking supersymmetry, right? Because
Slightly.
Because wait, what? W has to vanish for supersymmetry, right? So if R1 is not equal to R2, is that right?
dw
has no, to find the supersymmetric factor, there is a supersymmetric factor for the whole system.
Okay, but
see, the point is that even if you add these terms, you have the same number of Goldstone modes. So if you have the same number of Goldstone modes, and if you have the supersymmetry, or if you look at the other way around, if you have the same number of Goldsteins, you can say from here that
what's the formula for the vacuum energy in terms of W?
dw over d5.
dw, the standard thing, del W, del W, del phi, all square. And you have to do this for all the fields. And this is the F terms, and then there is this D term. Yeah, so as
I still didn't understand. How do you get this C1 to R1 minus?
No, that's what I'm saying. If you put this term, then you can show that given this, you have slight masses for these things. If you put
that term, you can show that there are masses for it.
That masses are exactly related to the C12s. And you know from this calculation, so basically maybe you know this calculation. So in a D0 D4 system, if you switch on constant B mu fields, you get this tachyon modes, right? All these Z's essentially become tachyon, slightly tachyon. If you keep this is very, very small. This is exactly what you will happen. This mass will exactly be written in terms of this.
Sorry, the masses, are they just the masses because brains are separating and the string has a length? Is that the mass you're talking about?
That is already arising from
that calculation. Yeah.
But you're saying what is the additional effect here?
No, that mass is what basically is created by this constant B mu and G mu. That is the mass that Sridhar is doing.
Where is the mass? He's trying to, if I understand, he's trying to understand this R1 minus R2 term on the third line.
There are other terms here.
And other terms, I guess. But let's just look at the R1 minus R2. So he's saying, how is that arising? And you were saying that if that is non-zero, R1 minus R2 is non-zero, you get a mass term.
No. Yeah, if it's non-zero. If you put C12 equal to 0, then you cannot consistently say that this system arises from a system in which you fluctuates
So that is what I think one was trying to understand. Right? Why can't you say that? Because you get an extra contribution.
Yeah, so as I said, so if you do not have these B mu fields in the D0 D4 system, if you quantize, you get exactly massless Z1.
Oh, I see. Wait, I think C is set by the B fields?
Yeah, C is set by the B fields.
Oh, I see. So I think that this question of why they're sitting together was just that there are B fields.
Yeah.
It's like the 0-4 system, right? If you take the 0-4 system and you put a B field,
this is
then there is no longer separation one.
Tilting force that you have if you have two brains, it will be tilted.
So just a constant B field.
Just a constant B field. Do that. This small instant on singularity is resolved by putting a B field. They don't meet it. This is very bad. So you're not working, because you're working at a generic point in moduli. And the generic point
is what I mean by a generic point. So some B mu, some G mu, in all of them switched on. No eta mu come here. Or putting B mu to 0.
Okay. So were you working at a special point in moduli space, C12 would be 0.
Yeah.
And then you would not have the isolated vacuum.
Yeah. Then you
will have the separations of this. Now I understand. Thank you.
Then you will get into problems.
Okay, good. It's good because had it been some subtle quantum superpotential, you would have to explain how you got
That's
So the point is that when we got the
classical, it's purely classical. Yeah.
Okay, a question from here.
Yeah.
So the C12, if it is a mass term, shouldn't there be a square with R1 minus R2 or is it inside as it is written?
No, this will get a mass term. There is a Z12 R1 minus R2 Z21 term. This and this C12 basically will give the mass for the Z21 thing.
Oh, okay.
So if you take the derivative with respect to R1 or R2, then you will get a term like ZZ minus C12. Whole thing mod square.
Okay.
That generates the mass.
Basically, it's, the point is that when you put B field on the D4 brain, 0 brain feels a force. Is attracted to it.
Yeah.
That's the thing.
Yeah, this is essentially just this one.
So how do you calculate the C12? I mean, what goes into the calculation of C12?
That is just a matching from this. We have an intuition that this has to happen. If you switch on this immune, there will be tachyonic modes or some masses. for these z's.
So you will relate it to the Monomial field, no doubt.
Yeah.
But
You can exactly calculate.
Huh?
You can exactly. We have an expression in our paper. I don't just want to write it.
What goes into that calculation? I mean, what is the calculation?
It is not very difficult. You know from here how the masses of these z's will depend on b mu nu, right? So basically, it is some b mu nu in two directions minus some epsilon mu nu. So basically, it goes like some b minus some epsilon b squared. Roughly speaking, without the indices.
I see. So you compare it the level
Compare
of
this
equation
with
of
this.
motion
C12
after
and then
the
solve it.
Okay.
And if you keep track of everything, you will see that the number of unfixed things here, the b mu nus and g mu nus, the number is 15, I think, and the number here also it will turn out to be 15. So there you can actually give one-to-one matching, but it is not one-to-one matching in the sense that there are much less number of massive fields here. So the number of equations are basically, I think, 6. So there are a lot of freedom as to how you should parameterize this. But that is not, till now I don't see any relevance for that, but the parameters match, number of parameters match. Okay, so let's move to the
You're technically over.
But isn't he still only on the intro?
There are too many questions, I guess.
So let's see till 1:15, 1:15. Another half an hour.
So in the abelian case, so after you do all these things, what you get are 12 z's. Of these 12 z's, you know that we have from the supersymmetry F terms and D terms. We also know that if you have D terms, you can substitute this D term in terms of a complexified gauge transformation. This is usual stuff people do. So you can always show that the D term is in one-to-one correspondence with a complexified U1 gauge transformation from here. And there are three such U1 gauge transformations, because one of the U1, the sum of all these U1s, is basically related to a gauge field which is the sum of all the gauge fields. And this basically is a zero mode. So one of the U1s basically is carried by the zero mode, and you have thrown away the zero mode, so you should throw away that U1. But remaining three U1s you complexify, and you basically will get this, so 12 minus 3, that is 9 gauge invariant. So basically the moduli space should be parameterized by gauge invariant operator, and this gauge basically I mean complexified gauge. And so you get 9 of them. There are at least two ways to do it. Either you by hand do a gauge fixing and basically find out, or you do it a more I think it is a better way. Better way is to parameterize in terms of gauge invariant variables, and you can easily write down gauge invariant variables. So suppose this Z2, 3, 3, 1 and 1, 2. This is a gauge invariant variable. So you have this kind of equations. You basically turn them to polynomial equations in gauge invariant variables, and you attempt to solve them, you get 12 from here. So because this is discrete number of solutions.
So this was also by everything U1. Yeah.
So because this is discrete number of solutions, you can make a further statement about the angular momentum. The statement is as follows. So the statement you should make is, because these are discrete solutions, the SU2 group, because this is quantum, so let's suppose start from the beginning. Because it was a supersymmetric quantum mechanics, the SU2 group in supersymmetric quantum mechanics basically makes it, basically changes the harmonic function. Do you remember? It is essentially...
This SU2 is in the R4, right?
Yeah. So basically it will be Q, SU, some Z3 into Q will be some another q into. So if you start with some state, then there will be another state which is q of 0, something like this. And this has zero angular momentum, this will have half angular momentum like this. So the SU2 basically acts like this here. So what it means is that if you have discrete points and you know that this basically directly corresponds to cohomology. This would have meant, if this was possible, this would have meant that you have a non-trivial cohomology in the system. A zero-dimensional system cannot have a non-trivial cohomology. There is no 1 form, 0 form, 2 form, nothing is here. So the only thing that makes sense is that they have zero angular. They are all symbols.
Actually, much of this went too fast for me. I asked you really going. Firstly, what is this 12 sets?
So for each of the pair of branes, you have 6 such pairs, right?
You have 6 sets. Yes.
So this is 6 into 2. So one brain is like that, one string is going like this, another have opposite orientation. So for each of them, there is a Z12 and then there is a Z21.
It's just because it's hypermultiplet.
These are hypermultiplet.
Yeah, fine. Okay.
N equal to hypermultiplet, so you have 12 with opposite conjugate charges.
Right. 12 N equals 1.
Standard structure.
Okay, great. Plus 3 complexified gate symmetries, because you're saying relatively one. Right? So the overall one doesn't have. And therefore 9 gauge invariant variables. And these are the 9s are the
So these
triples of.
So these are 6 equations. So ij is going from 1 to 4, but it doesn't matter whether it is ji or ij, because the cij is basically symmetrical like this. So these are 6 equations and 3 equations here. Total 9 equations. 9 equations is 9 variables.
And can I see these 9 variables in this compound language, the gauge invariant language?
In U language?
In the language of gauge invariant.
Oh, I think I have not written.
But I just want to know, can you write down these variables or are there relations? Which from where, please?
Oh, these are this. If you remember, these are this Z, phi, Z, and this C125. If you take this del phi, you get Z.
Fine. And those equations came from where? Schematically, the remaining 3?
Schematically, it was, I think, other terms were there. So there was this Z superpotential term. A lot of them came from not exactly there. So there was this Z, and then there was this phi Z. So I think one of the Z's, if you take a derivative among one of the Z, you get relations among phi Z and some ZZs. Then you have to replace this phi.
I see. Some complicated thing. But I want to know, was it obvious before looking at it that there would be 9 equations, or that's something you had to work out?
Obvious from the... No.
You had to work out. Or it was clear that there would be 9 equations?
It was clear that it was 9 equations.
Why is it clear? Just take it as that. I mean, it's very important for you that you have as many equations as variables, right? I just want to understand whether that's what some structural thing or something you have to understand.
I mean, just on the basis of gauge invariance, you could have something like Z23, Z31, Z13.
Yeah, it could have a lot of other things.
I mean, as long as the indices match, right? The successive indices match.
Yeah,
you have
I can have a long string of.
You can have a long string of such things, but presumably, as you have said,
related to the
small or related to this small number of variables.
Yeah, unless that happens, you really do not have this vacuum manifold parameterized by. They have to be independent of each other.
Is that clear why it happens?
Why?
I mean, why are there these number of independent?
I think for this U1 case you can show, but
I'm sorry, this goes way back to stuff I did, but I can't remember. There's a general result in n equals 1 that if you have an R symmetry, then the number of equations you get are the number of variables. Just from now I don't know if you effectively have
I
R
do not
symmetry.
think we have a.
Okay, then we'll have to look exactly what has happened. This is the kind of thing that's been thought about a lot in Susie breaking also, because
Nelson, something.
Exactly. So you don't have. I was also thinking, because you have one term R1 minus R2. I don't see an obvious.
Yeah, I don't. So because the Z couplings are there, so I don't think there is RC.
So I agree. It wasn't obvious to me also. But okay, so we'll have to.
Okay,
yeah. To your answer, I do not think it was too obvious, because this is the final form of the equations that came from doing some manipulations, equations like this.
Right.
So I don't think it was completely obvious that you will get 9 equations.
Right, but is this a generic situation that you expect as many equations as variables? That some fine tuning has to happen for this not to be true, or sorry for my ignorance, just to.
You can always say that from first principle you know that you should be getting microstate switch.
No, I don't think that. Let me just put generic quantum mechanics. That if you put the most arbitrary superpotential without thinking very much, would you expect to get as many equations as variables? Presumably, right?
If you just do rapidly, of course the answer is yes.
Yeah.
But then the question is, if you have a gauge theory, then you have to factor out the complexified gauge transformations and then do it. And then it's more tricky. But there is quite a lot known about when you get as many equations. I can't recall fabulous stories, sorry, but there's some stuff known.
Okay, sorry for slowing it down. And now you were saying something about SU2, which because I was thinking about this, I totally didn't get it. So please say that again.
Okay, so if you have this quantum mechanics, Susie quantum mechanics, if you have. So basically, you will have a down state, and then you can have states which act Q1 acting on these ground states.
Yes.
You have a multiplet of these states, right? So how these two are related? So if this has a zero angular momentum, it will have a half angular momentum.
Yes.
So there is a SU2 sitting there, which has a charge J3, and basically is controlling this going up and down in this level, right? So the point is that and these things are exactly related to homologies of the 1 form, 2 form, 3 form, etc. Higher homologies of this Kaplan manifold.
What thing is related to that?
So from this.
So Q is sort of D on that.
Yeah, Q is D basically. So basically you have DG equal to 0, and then if you have lots of Q1 and Q2, then those things basically becomes a higher homology than a single Q.
So higher cohomology than a single Q. So
maybe I'm using the term wrong. I mean 1 form, 2 form.
You're checking to see that the only scalars.
Yeah, so the harmonic forms.
Right.
Okay. So these have direct relations. Because this Q is D, you have a direct relation. If you have to have states which basically preserve supersymmetry, those states are essentially harmonic forms.
Correct. They are harmonic forms in the space.
Yeah. So because they are harmonic forms, they basically have to have either they are 1 form, 2 form, or 3 form, something like this, right? So now the point is that because we are getting zero solutions and just points as a solution, there is no homology in this space.
You think that the space is zero dimension.
So that only means that you can only have singlets under the SU2. You cannot, by any chance, generate this. This basically then says that all the states that you are getting are zero.
I'm sorry to slow you down so much, but I still haven't clearly understood the connection between having higher forms and non-zero angular momentum under the SU2. Please say that again.
Yeah, so
could you have some higher form that was zero angular momentum in the SU2?
No, all these things have to be representations of this, right?
I see. You're saying the only thing that carries SU2 in this is that the vacuum has zero SU2.
Yeah, so anything that will carry SU2 a non-trivial Z3 eigenvalue will have a multiplet associated.
You're saying a form, like a 1 form is necessarily spin half?
Yeah, it has to.
Under SU2. And a 2 form is some combination of...
Yeah. So it depends upon how you normalize, but it is not singlets.
We just sort of, if you just thought about these as harmonic forms on the internal manifold, first, then you don't see why they should be charged.
Exactly.
Then you think in terms of Q,
Yeah.
then of course they should be charged. So there is something non-trivial going on, which is interesting.
And even that's not totally clear to me. I mean, you don't have to build a one form by acting with Q. You can have a one form, and then you want to check whether that one form is the cohomology of Q.
So to begin with, we do not have the manifold, right? We know that we have a supersymmetric quantum mechanics. We know that if you get a vacuum manifold, we know that there is a relation between the Euler forms on this vacuum manifold, like this
Understand? I understand.
forms in this vacuum manifold to this.
So suppose you had a vacuum manifold with a non-trivial one.
Yeah. So
I cannot yet say, I'm sorry, that being stupid, but I cannot see why the one form had to have an SU2 angular momentum. I understand that the Q operator has SU2 angular momentum half. How does it follow from there that any one form on this manifold has SU2 angular momentum?
Okay, so if you have any non-trivial vacuum manifold,
Correct.
it will have presumably a top form and a top form.
Correct.
And a zero form.
Correct.
Right? So if you have a top form, to begin with from the top form, you can make this Q, the lowering operators for the Q's and go to other things.
Lowering operators for the Q's.
So basically,
Q access B, right? The end of story.
okay.
So you've got some forms, Q access B. Now,
That's where the puzzle is. If you were to act as B, why would it have a SU2 angular?
Maybe I was
why would Q has an SU2 angular?
Yeah, what I'm saying.
Okay, yeah, why is it? Yeah.
That is the sort of conflict.
Yeah.
What is the
Okay, if you just had various forms on the internal manifold, then the action of D is something which doesn't carry SU2 angular momentum vis-a-vis R4. D is, okay, you have some.
D is Q here, suppose.
But Q does carry SU2 angular momentum, right?
Yeah, half.
So there is in my mind, I'm not able to map the two as clearly as I should to give
Yeah.
a message around.
Yeah, and sorry, so is this the case? How many supersymmetries do we have?
4.
4. So you have 2 Qs and 2 Q bars. Is that right?
2 Q's.
So this is the case of complex geometry. There's a D bar, a del bar, and then the complex.
I guess so, yeah.
And maybe the SU2 is that. Is that some? I know this already. Maybe it is. Yeah. Okay, good.
So now the non-abelian case. So nice method to do the non-abelian case will be a Hilbert series computation, which I will come to later. But yeah, we didn't manage to do it in complete generalization because some computational limitations. We don't know how to do it. But I still think that is the best way to go because doing things in Mathematica.
Just to ask, do you know the superpotential for the non-abelian case?
The whole thing we know.
You know,
We
right?
just have to
So
solve
it's
it.
just a question of finding the manifold of whatever of solution.
Yeah.
Again, you can parameterize it in terms of gauge invariance. If you couldn't solve that.
Yeah, that is what I'm going to talk about because I think that is important because we have to ultimately move to that only. Whether we could solve it now or solve it one year later, but we have to solve it that way. The point is that for these cases, for these small cases 1112 and 1113, after a lot of gauge fixing and other things, it was somehow barely solvable in Mathematica, and I also checked by some other some variant of the Hilbert series methods that the answers basically from the Hilbert series and these things matches. So that is not the problem. But the problem is what if I want to go to 1114, 5, 6 or any 1122, anything, or any 182 and 3 and 4 general. Mathematica cannot handle this. Neither can any computational algebra system can handle that many polynomial equations in that many variables. More or less impossible. So the only
just to go back to what you said, again, I'm a little lazy, but there's a general argument, as you said, that if you cast it in terms of gauge invariance and you find a solution that way, it automatically solves all the D-term conditions.
Yeah, so maybe I can now.
Okay, later on.
I can keep.
We hit lunch as the heart.
I can, yeah. So to answer Siraj's question about this thing that whether number of equations are same or not, and that is true because if you have this superpotential W, all the z's and phi's are coming in the superpotential. So if you take derivatives in respect to z's and phi's, you get all the equations for z's and phi's, and that is how we know basically.
Yeah.
That will be a zero-dimensional system unless somehow non-trivially two of the equations become same.
Okay, but that's right. But that wouldn't happen generically.
Generically, it should not.
But the only so what the argument you give is definitely true in an O-Rafferty model, and the only subtlety here is that your elementary fields carry color indices, and you have the D-term condition. So that is the only non-trivial thing which you have to answer. But there's well-known technology to understand.
Yeah. So the main non-trivial thing is that I would say we have 60, 70, 80 equations and 80 equations to solve. And in the most
Your gauge invariants are fewer. Your gauge invariants are
quite fewer actually.
Yeah,
so this is, you can see U1,
No, exactly.
another U2, another U3.
Exactly. So
basically, the point is that it doesn't really help if you go on increasing up to UN, because with UN you will also have a n cross n extra multiply these things, right? So all the phi's will become n cross n matrices, all the z's will become columns of 1 to n, and the number of gauge fixing is much less than actually. So that is the basic complication. So the point is that, okay, so for these cases, at least this works with the correct sign in the ZZ.
Abhishek, I'm sorry for all the questions, for 10-15 minutes, I think.
That is impossible.
We like go over lunch. Try to speed up as much.
Okay. So yeah, so as I mentioned earlier, so there is a correct sign of ZZZ up to an overall negative sign in the phi-phi coupling, which we basically fix by saying that this negative sign basically gives the correct solution. This basically gives the correct solutions. And these signs basically, I am not going to tell, but these signs are basically fixed by various discrete symmetries. So basically, these discrete symmetries are nothing but if you say, I have brane 1 and brane 2, who says that you should label brane 1 by 4, 5 coordinates and brane 2 by 6, 7 coordinates. You can swap them. And all the superpotentials should be invariant under them. And it is non-trivial that because if you do this kind of things, because the B mu news and G mu news are there in the C1, C12, C23, these things, they basically picks up signs. So you have to compensate those signs by giving commensurate signs to all the phi's and z's, and you have to do that consistently. So, but you can do this, and after you do, you basically find out what is the consistent signs.
So maybe I should ask now. So if you turn on a B mu field, then you are turning on some particular choice of B mu field, right?
I am just demanding B mu to be small, and it can be arbitrarily anything.
What I'm saying, it would typically break the symmetry between the directions, because you're turning on some B mu field. I mean, the way we did that, for example, is to do this duality and rotation and stuff. So I have to pick. I
was saying that these B fields are connected to the angles of the branes and those stuff.
Yeah, the B fields generally would break the symmetry between this.
Yeah, some sort of angle is basically the B fields.
Yeah, what you call 4, 5, 6, 7, and 8, 9. These directions. Yeah. So this perfectly symmetric superpotential which you have.
Yeah.
Why should that be the case?
Maybe the
we can
involves,
discuss this. We can
involves switching the C's as well.
No C's.
The C's which were the B's. The CIK, whatever.
No, but they are fixed in terms of the B's.
So that's what Gautam's saying. Gautam's saying there's no symmetry if you turn on B's, but if you change the B's when you do the symmetry, then there would be a symmetry. Like you change the coupling.
if you think of the, I see.
Yeah.
I see. Together, I see. So the C's are taking part in this.
I would imagine.
Yeah. C's, yeah. That's what I'm saying.
Okay.
C's will change sign. because to compensate the change of sign of C's, you have to change signs of phi's and z's. That it is an iterative process. You have to do it consistently. After 2-3 runs, you will get all the signs correctly.
Got it. Yeah.
So towards the conjecture. So the conjecture here is basically that this microstate basically carries zero angular momentum. So yeah, so matching of this index does not really imply that it should be a one-to-one match with the microstates. So as I mentioned earlier, there are lots of microstates, but somehow there is a decision cancellation.
Abhishek, I suggest you go fast.
Yeah, I think I will stop before the Hilbert series. I don't have time, so I will stop here.
There's always NSM, as you said.
Yeah. In gravity side, yeah, so basically I mentioned this thing that you have zero angular momentum in gravity side, that is why you should think that you should also have this here. And in our work also we have found this zero angular momentum state. So the suspicion is that whether this is generic or not. So what we know so far, it doesn't contradict to say that this should be generic, in the sense that when black holes are valid, as I already mentioned, microstates or single center black holes can carry only zero angular momentum because the microstates basically can be the same. And so in the normal calculations that we have in the literature, there are lots of cancellations. That also doesn't really contradict anything that we are saying. But what we are saying is essentially that what we are doing is at a very generic point in the moduli space. And this is something not done in the earlier calculations. They all did it in a special point. And maybe that is the reason why they have all these extra angular momentum states, which ultimately do not contribute, but they are there. And as I also mentioned on the first ball, this is the equations. So how can you give me 50 minutes? 15.
Okay.
Okay, let me go through. So yeah, this is okay. So this is precursor to Hilbert series. So basically, you have a polynomial ring, which basically means you have polynomials in this x1 to xn over some complex field C, and you denote it by something like this. They form a ring. I'm not going into details. I don't have time for this. And then the set of fields. Then you can define something. Okay. So there is an ideal. Ideal basically means some relations on these polynomials, and it basically says that if there are polynomials E1 to Ek, which basically should be thought of as generators of the ideal, then any Fi from this polynomial set, if you multiply this, should also be in the ideal.
I am. What is Fi?
Fi is anything from this C. So if you have some polynomial, Ei, you multiply by any Fi here.
Yeah.
It should also be on the ideal.
Ideal is okay. Please go on.
One possibility is maybe there can be a talk in the afternoon.
Yeah, so this is also actually going to
I may
take
not be
some
able to
time.
come, but
I can talk basically. I have the material.
You're also here on Thursday, right?
No, not Thursday. I am leaving on 3rd.
3rd is Wednesday. Tomorrow, Ronak is talking. Is that right? Gautam, Sandeep was suggesting we continue the talk on another day. Because
just because
I also need to
especially
I cannot finish this in 15 minutes. I cannot finish this in 15 minutes.
You want to understand.
Yeah,
that's true. So I either skipped or waited properly. I mean, it's no point. Yeah.
Sure.
Did we have a slot?
So this Thursday, I don't remember what this.
Thursday is free, but he's not here. Wednesday, are you here?
Wednesday is 3rd.
Yes. What time are you going?
Wednesday is 2nd. Wednesday is 2nd.
Right?
2nd. Yeah, I am going on 3rd afternoon. Going to Pune.
Is Wednesday morning okay for you? Today is a bit exhausting for me.
I'll try to come Wednesday morning. I can't guarantee this is a faculty meeting, so I have to. What did you say?
Wednesday morning class.
Classrooms. We don't need.
The room we can understand.
Yeah, somehow.
I think you'll get a room because there's a faculty meeting, so nobody else will be doing academic activities.
Sorry.
Well, my suggestion is if you're here on Wednesday,
Yeah, I'm here. I can give a talk.
Wednesday morning is not free.
all from 10 onwards.
To me and get up.
No, classes are probably over.
No, twins classes probably not continuing.
Yeah.
I mean, twins classes are over.
Only students is continue to teach after teaching. So, yeah, I'm sure we'll manage. Yeah, let's.
I think then try. I would suggest that's better.
Wednesday morning is fine with me.
Yeah. Let's say tentatively.
Yeah, fine with me.
Yeah, we'll send already.
Yeah, anyway, this should take some more time.
Okay, do you want to say some concluding remarks? Hey, ICTS, I'm sorry about this, but the strategy is to continue the talk at an ideal time on Wednesday.
An idea.
I have more or less explained that what we wanted to do, right?
Yes.
So ultimately, we wanted to go to Tel Aviv House, and basically we wanted to go through the Hilbert series procedure. So I will mention the procedure if it will give me time. On Wednesday. Okay.
As music.
Who the hell is Roy H.B.?
Some philosopher. Not a strict theorist, let me change.
Okay, sorry, questions, ICTS?
No questions. Yeah.